Let's say we have a first order reaction where A turns into our products. And when time is equal to 0, we have our initial concentration of A. And after some time t, we have the concentration of A at that time t. And let's go ahead and write out the rate for our reaction. In an earlier video, we said we could express the rate of our reaction in terms of the disappearance of A. So we said that's the change in the concentration of A over the change in time. And we put a negative sign in here to give us a positive value for the rate. We could also write out the rate law. So for the rate law, the rate is equal to the rate constant K times the concentration of A, and since this is a first order reaction, this would be to the first power. So we talked about this in an earlier video. We can set these equal to each other, right? Since they're both equal to the rate, we can say that the rate of disappearance of A, so the negative change in the concentration of A over the change in time, is equal to the rate constant K times the concentration of A to the first power. This is the average rate of reaction over here on the left, and so if we wanted to write this as the instantaneous rate, we need to think about calculus. Right, so the instantaneous rate would be negative dA, right? dA, the negative rate of change of A with respect to time. So this would be dt, and this is equal to K A to the first power. And now we have a differential equation. And when you're solving a differential equation, eventually you get to a function, and our function would be the concentration as a function of time. So we'll eventually get there. But your first step for solving a differential equation is to separate your variables. So you need to put all the a's on one side, and we'll put the t on the opposite side. So we need to divide through by a. So we get, on the left side, we divide both sides by a, and we get dA over the concentration of A here. We're going to multiply both sides by dt to get the t on the right side. So we would get K dt over here on the right. And I'll go ahead and put the negative sign on the right as well. So we just rearranged a few things to get us ready for integration. Right? After you separate your variables, you need to integrate. So we're going to integrate the left, and since K is a constant, I can pull it out of my integral, and I can go like that. And let's see, what would we be integrating from? Well, for time, let's go back up to here. Right, time, we'd be integrating from time is equal to 0 to time is equal to t. And for concentration, we'd be integrating from the initial concentration to the concentration at some time t. So let's go ahead and plug those in. So we'd be integrating from 0 to t on the right side. On the left side, we'd be integrating from the initial concentration of A to the final concentration, or I should say the concentration of A at any time t. All right, so on the left, right, dA over A, that's natural log of A, right? So that would be equal to the natural log of A, and we would be evaluating this from the initial concentration to the concentration at some time t. And on the right side, integral of dt is just t. So we have negative kt evaluated from 0 to t. Next, we use the fundamental theorem of calculus. So on the left side, we would have natural log of the concentration of A at some time t minus the natural log of A, minus the natural log of the initial concentration of A. And then on the right side, we would have negative kt. And so this is one way to write the integrated rate law. So on the current AP Chem formula sheet, right, this is your equation for a first order reaction. So this is your integrated rate law, your integrated rate law. And this is one way to write it. You could keep on going and express this in a different way, which we'll do in a later video. But this is one equation that you can use to solve some problems here. And let's go ahead and rearrange that a little bit. All right, let's add the natural log of the initial concentration to the right side. So let's rearrange that, and therefore we get natural log of the concentration of A at some time t is equal to negative kt plus the natural log of the concentration of the initial concentration of A. And the reason why I wanted to rearrange this is so you can see that this follows the graph of a straight line. Think about y is equal to mx plus b. Right, so we know that y is equal to mx plus b is the graph of a straight line. And if you think about what you would need to graph here, right, you would put the natural log of a, right, on your y-axis, and on your x-axis you would put time, right? And then we can see that m, which is the slope, would be equal to negative k, and b, of course, is your y-intercept. And so that should be the natural log of the initial concentration of a. And so if we put together a little graph here, let me just real quickly sketch in a graph. So we would have, let's say that's our y-axis here, right? So here's our y-axis, and then we would have our x-axis right here. All right, and let's go ahead and label our axes. So for our y-axis, we put over here on the left, this would be the natural log of the concentration of A at any time t. And then on our x-axis, we would put time. Right? So here's what we're graphing. And then the graph of this should be a straight line. Right? So the graph is going to be a straight line. Let me go ahead and draw it in right here. So I'm just going to attempt to sketch a straight line in here like that. And this would be our y-intercept. Right? And our y-intercept should be the natural log of the initial concentration of A. Right? So this point right here, our y-intercept, should be the natural log of the initial concentration of A. And the slope of our line, right, let's go back over here, the slope of our line, which is m, should be equal to negative k. So if you get the slope of this line, this slope is equal to negative k. So from the slope, you can find the rate constant. And the graph of the natural log of a versus time gives a straight line with a slope of negative k.